In this video, we will discuss atomic physics. In the 20th century, scientists noticed that when metal was subjected to light rays, it emitted electrons and sparked. They also noticed that below a specific frequency, changing the intensity of the light rays did not cause an emission. That is, if the frequency was too low, a high or low intensity did not cause an emission. Of course, changing the intensity happens by changing the amplitude. This phenomenon of electron emission is called the photoelectric effect, and it defied the wave theory of light, because as a wave, light should not be able to remove electrons from an atom. The photoelectric effect begot the quantum theory, which was made by Albert Einstein. Einstein said that light is made of photons. Photons are small, quantized packets of energy. We said that below a specific frequency, no electrons were emitted from the atom. This frequency is called the threshold frequency. Below the threshold frequency, electrons did not leave the atom. However, when the frequency of photons surpassed that of the threshold frequency, electrons were emitted from the atom, and frequency of photons is directly proportional to the kinetic energy of the emitted electrons. The slope of this energy frequency graph is 6.63 times 10 to the power of negative 34 joules per hertz, or joule seconds. This constant is called Planck's constant, and it is a very small number and is symbolized by the letter H. To find the kinetic energy of the emitted electrons, we use this equation. Kinetic energy equals to H frequency minus H threshold frequency. H frequency is the energy of the photon that caused the emission. H threshold frequency is called the work function. Because each metal has different threshold frequency, each metal has a different work function. The work function is sometimes written in this way, and at other times it is symbolized by the letter phi. However, these three equations are equivalent. They actually are the same equation. Using this information, Albert Einstein concluded the dual nature of light. That is, light existed as both a particle and a wave. Light is not a particle or a wave, it's both. Arthur Compton conducted an experiment on graphite and X-ray photons. He noticed that when X-ray photons collide with electrons, as the electrons were emitted by the photoelectric effect, the photons were scattered. This scattering of photons is referred to as Compton Effect. The scattered photons had less frequency than they originally did before the collision. And because frequency is directly proportional to energy, they definitely had less energy than they originally did. Now, to understand this, we would see that the energy of the X-ray photon was mostly given to the scattered electron, and only a small amount remained in the scattered X-ray photon. This means that energy is conserved, and when energy is conserved, momentum is conserved. So, X-ray photons have momentum. Arthur Compton found the momentum of X-ray photons to equal Planck's constant over the wavelength. For particles with mass, like you, me, electrons, and protons, momentum equals to mass times velocity. However, photons are waves and they don't have mass. So, their momentum does not equal mass times velocity. It equals h over wavelength. Again, momentum equals h over wavelength. So now we know that light, a wave that has wavelength and no mass, has momentum. Could particles that have mass or momentum, or in other words, matter, have wavelength? This question was answered by Louis de Broglie. Louis conducted an experiment using electrons. This experiment was similar to Young's double-slit experiment. However, instead of using light, he used electrons. The electrons were diffracted through the double slit, and they made an interference pattern similar to that light has made. So, electrons could diffract and interfere. And these are properties of waves. So yes, electrons could act as waves, and they could have wavelength. He used this equation for the momentum of photons to find another equation for the wavelength of electrons. Because wavelength equals to Planck's constant over momentum for photons, this same rule could apply for electrons. So yes, wavelength equals to Planck's constant over momentum, and for electrons which do have mass, momentum equals to mass times velocity. So, for photons, momentum equals to h over wavelength. For matter, wavelength equals to h over momentum, or h over mass times velocity. As you see in this equation, wavelength is inversely proportional to mass. So, an object must have very small mass to have a considerable wavelength. This wavelength, which is for matter, is called the Bro's wavelength. So, photons and light have normal wavelength. Matter, like electrons and protons, have the Bro wavelength. And they should have a very small mass to have a considerable wavelength. A small mass is like that of an electron, a neutron, or a proton. And while a baby's mass is relatively small, a baby is definitely not small enough. One last scientist is Heisenberg. Heisenberg is famous for his uncertainty principle. He says, because of the wave nature of small particles, that is, electrons, neutrons, and protons, it's impossible to determine precisely both the simultaneous position and momentum of a particle. That is, if you know the momentum, you cannot know the position, and vice versa. So, to review the rules we studied today, kinetic energy of an emitted electron equals to h times the frequency of the photon minus the work function, which is h times the threshold frequency. Momentum of a photon equals to Planck's constant over wavelength, and de Bro's wavelength, which is the wavelength of small particles of matter, equals to Planck's constant over momentum, which equals to mass times velocity. That's all. Thank you for watching. Do not forget to subscribe, like, and always achieve more. Thank you.